Hello, this is the second video of nutrition and metabolism. This is the nutrition half, so I should have called it metabolism and nutrition, but some of the stuff you know undoubtedly. So I'm going to start off with major nutrients. You can, whenever you hear carbohydrates, lipids, and proteins, the first thing you think of are foods. That's true, but you are made of those, right? So you're literally made of your food. You are literally what you eat. There's no molecule in you that the vast majority of which you've consumed in food over one point of your life. So you have ways of taking food, breaking it down, rebuilding it back into you. Let's start with carbohydrates. This is your main energy source, meaning that you're going to drive most of your calories, as per that previous lecture on cellular respiration. Most of your calories and conversions into ATP are done from carbohydrates. But you can also take carbohydrates if you eat a bunch of them and convert them to other things, right? So you store up this molecule called glycogen, which you know in your liver and your muscles if you've got a surplus. And you can also, if you've got a big surplus, you're going to turn sugars, carbohydrates into fats. You can get fat eating no fat because you have the ability to make fat. Now a couple of oddball carbohydrates down here, cellulose and pectin. You may have heard of both of them or neither. Cellulose is insoluble fiber, so that dietary fiber line on your nutrition label on your food, that's what that is. Now it's insoluble, and also that means it's not soluble in water, but it's also, we can't digest it. We can't break it down. We don't have the enzyme that'll take cellulose and decompose it. If we could, it would be sugar. We got glucose. That's all it's made of. But what we've adapted to use it for, as it's been in our diet for millions and millions of years, we've basically we've used it now to kind of brush out our intestines. So if you've got a really high fiber diet, that tends to keep your gut clean and ultimately reduce the chances of various colon cancers and so on. So try and get a higher fiber diet than you probably are getting. You're probably not getting enough. Don't eat white bread. Try to lay off the white rice. If you're just eating carbs, try and get some fiber carbs, like get the whole grain stuff. Pectin is soluble fiber. These are those little gummy fibers that you might see in the market. And what these are good for, what this fiber is good for, is for cholesterol reduction. So it tends to keep a check on your cholesterol levels. Speaking of cholesterol, let's go to the next class of molecules. And these are lipids. So the majority of lipids are fats and oils. That's what we normally consume them as. Those fats and oils are called triglycerides. So the majority of the lipids that you get in your diet are this group called triglycerides. And triglycerides have these fatty acid tails. I'm just going to kind of draw this in here. They got these fatty acid tails that kind of dangle off the glycerol group, and there's 3 of them. And if it's a saturated fat, these fatty acid tails are all on these nice straight lines, and they're called saturated in that they don't have any double bonds. There's no room to add. There's no basic open space in any of the bonds. They're all single bonded, and they tend to lay flat on each other. These saturated fats are the worst for you because your body will generally try to store those. So if you eat a lot of saturated fats compared to unsaturated fats, usually those are earmarked for storage, so around the belly or around the organs. Unsaturated fats are a little bit more easy to metabolize. They have double bonds. If you've ever seen mono or poly unsaturated fats, mono just means that there's one double bond, poly, many double bonds. These tend to be oils, right? So plant lipids are most often unsaturated fats, and they tend to be liquid at room temperature. That's the dietary difference between fats and oils. Doesn't really make any sense. Well, it makes sense chemically, but it's not that useful chemically. So lipids in general include triglycerides, like I'd mentioned, but they also include things like steroids. So steroids we think of as hormones, and there are a lot of uses for steroids as hormones. But one steroid is cholesterol, and you know that cholesterol, when you think cholesterol, you think, well, we want to reduce our cholesterol. And there's different types of cholesterol. There's the good cholesterols, which you like to have higher levels of, and bad cholesterols, LDLs. I'm not going to go into that, but those are those are not as good for your cardiovascular system. You can make lipids. So lipogenesis is manufacture of lipids, like when I mentioned when I was talking about carbohydrates. I could eat, pixie sticks all day. That's just all sugar. Is pixie sticks the ones with the little powder inside? No. Is it? Pixie stick? Yeah, pixie sticks are the little powder tubes, right? That's just sugar. So if I ate like 5,000 calories of that every day, I would convert a lot of those sugars, the molecules in the sugars into fats. And then lipolysis, you can look at the other side of the coin, and you can break down lipids. And so if you're running a calorie deficit day after day after day, if you're consuming fewer calories than you're burning, you're going to probably have a net rate of lipolysis. You'll actually lose weight, you'll lose fat. And that's how that works. Easier said than done, right? Proteins, little summary figures here. Proteins are made of amino acids. You produce them in a process called protein synthesis, proteins that is. And if you remember that from A&P 1, I believe it was, you'd have transcription and translation, and then proteins are the result. Now, the amino acids, you only have 20 of them basically that make up all of our proteins. 12 out of those 20 you can make yourself. So those are called non-essential. It's kind of a weird name for it. You need them, but you can make them. 8 of them, the other 8, are what are called essential amino acids. So those you have to consume. If you're a meat eater, if you've got an omnivorous diet, you're going to get enough amino acids to make all of your proteins. But if you're a vegetarian or a vegan especially, you got to be a little bit careful because there's a lot of incomplete proteins out there in the plant world. So if you're eating a lot of corn, you're going to get one suite of amino acids. If you're eating a lot of beans, you're going to get a different suite. If you eat both, you're probably going to get all of them. So if you're vegan, be careful about your diet, but if you're vegan, you probably already know about it. You need calories for this. So in order to make proteins, I have to have enough calories. That whole thing I talked about with cell respiration, if you're not getting enough ATP, you are not getting enough energy to survive, right? So you're going to start throwing molecules into that burner, into that furnace, to get the ATP you need. So if you've got a surplus of calories, you can make enough ATP to make proteins, synthesize proteins. If you consume, let's say you're consuming a bunch of proteins, right? Or making a bunch and consuming a bunch, those aren't stored. So if you say, oh, I need protein powder, and you look at the scoop and it says one scoop is, 20 grams of protein, 2 scoops is 40 grams. Then you mix that with milk, so maybe you're up to like 50 grams of protein or something like that. And you're not working out so hard that you're gonna need those amino acids and those proteins to help rebuild muscle. At the end of the day, you're not gonna store those proteins away anywhere. You don't have a protein bank that you're gonna keep them in for later use. These are a use it or lose it type thing, and the way you lose it is you convert it to fat. So I could eat 5,000 calories of amino acids and proteins every day, and if I only worked out to the tune of 2,000 calories, I'm gonna convert 3,000 calories worth of stuff into fat. So keep that in mind when you're eating those expensive protein powders. If you are calorie deficient, if you're starving, okay? If you're not starving like, man, I'm starving, I could eat whatever. If you're in starvation mode, you're gonna break down those proteins. So here's the kind of sequence. Like I've got a little bit of extra, but if I went on if I started fasting right now, the first thing I would do is I'd deplete my blood sugar. Then I'd start pulling out glycogen, which is that storage carbohydrate. I'd pull that out from my liver, pull that out from my muscles. Once I got through that, I'd start working on those lipids. So I'd start losing fat, right? And now I'm not losing it, I'm burning it for calories. I'm burning it for ATP. And if I go through all of my fat, then I have to start burning the thing that I'm made of. And proteins are your main structural, functional molecules. So if I'm in real starvation mode, I'm gonna start catabolizing my skeletal muscle. And if I starve hard enough, I'm going to start catabolizing smooth muscle and cardiac muscle. So you're going to die eventually from consuming the house that you're made of. Does that make sense? So that's what starvation is. It's miserable. I have experienced it, but that's what it looks like. There's some other nutrients, vitamins and minerals, we've all heard of those. You don't need them in nearly the same quantities, trace amounts. You really don't need to eat vitamins for the most part. Those store-bought vitamins and mineral supplements are most of the time a little superfluous. If you've got a well-rounded diet, you're probably getting plenty of vitamins. The exceptions, of course, abound. But you get vitamins in food. These are organic molecules. Their functions are varied, but one of their main functions is as coenzymes. So if you remember, enzymes are molecules that catalyze reactions. Sometimes they need little molecular helpers to do it efficiently. So many of your vitamins, like you've heard of coenzyme Q10 or CoQ10, that's a coenzyme that helps another enzyme work. They also can act as antioxidants. Oxidation of your tissues can damage them. So there's those so-called free radicals that can, basically act like little billiard balls and knock your molecules around. And these antioxidant molecules tend to absorb those free radicals rather than your tissues absorbing them. Vitamins can be either fat-soluble or water-soluble. The fat-soluble ones, there's only 4 of. Vitamins A, D, E, and K. Those are the vitamins that you don't want to take giant doses of because they cannot be flushed from your system very readily. So if you consume a large amount of one of these vitamins, a really seriously large amount, you can actually overdose and die from that. There's signs of overconsumption of these vitamins, but for the most part, the volumes that we eat aren't going to be a problem. Water-soluble vitamins are more easily flushed, so vitamins like B and C and things like that you can take super big doses of those and make really expensive urine, which is what you do when you take, if you've ever eaten a big multivitamin or a super dose of one of those vitamin B supplements, you'll notice that not only does your skin itch, but you're going to produce some really bright yellow pee. Like it's going to really be shock color, right? That's vitamins in there. That's just, they flowed through you and you got rid of them. So you might want to, refine that and make another vitamin out of it. Just joking. Minerals, these are inorganic. Minerals, you can think of magnesium, calcium, iron, phosphorus, any of the things that you might see on the nutrition label. And they have a myriad different functions. They also help enzymes, and they're called, when the mineral helps an enzyme, it's called a cofactor. When a vitamin helps an enzyme, it's called a coenzyme. But minerals are also structural. Think of calcium. Most of my composition of my bone is calcium phosphate salt. So 2 different elements forming a mineral that I build into bone. But you can think of a lot of the chemical components of other structural elements being composed of minerals as well. But lots of other functions. All right, moving on. We've just eaten all these nutrients, and we enter what's called an absorptive state. That's A-B-S-O-R-P-T-I, that's supposed to be an R. Absorptive state. So this is after eating. I've filled my stomach with food. So I'm going to be absorbing the food, processing it in my liver, determining where to put the calories, where to put the different organic molecules, if I need proteins here or there, if I want to store fats, and so on. So the general type of metabolism that dominates during your absorptive state is anabolic reactions, anabolism. So I'm going to produce glycogen. I'm going to make glycogen out of all the extra sugar I have, and that's called glycogenesis. So glycogenesis is caused by insulin. This is one of the hormones we learned about early in the semester. Insulin lowers blood sugar levels. How does it lower them? It just doesn't turn down the thermostat. It has to turn glucose into something, and what it does is it's turning it into glycogen. You can also conduct lipogenesis. If you've got a chronic calorie surplus, if you're eating more calories than you're burning off, you are going to convert a lot of those molecules into lipids, particularly right after you've eaten them in that absorptive state. Now, if you go on a fast, you're going to be in what's called a post-absorptive state. And this can be, hours. It can be days, right, depending on how long you're fasting. If you're doing one of those intermittent fasting things where you only eat between, I don't even know, I've never tried it, but like after 5 p.m. or something like that, and then you go the whole next day and just do the same thing. Maybe you eat something in the morning and then way late at night. Or if you're observing religious fasting where you can't eat for the entire day period, say you're going to be solidly in that post-absorptive state. Or if you're just starving, right? I mean, if you're not eating, if you're on a hunger strike voluntarily or involuntarily, you're in a post-absorptive state. That, in this state, catabolism dominates. So catabolic reactions, those break big molecules down into smaller molecules. Well, I'm made of big molecules. If I'm trying to lose weight, that's a good thing, right? Because then I'm going to be breaking the large lipid molecules down into small subunits, which I'm going to use for energy. However, if I'm starving, then I don't like this whole catabolic state thing that I'm in, because then I'm going to be breaking down my lipids till I'm out, and then I'm going to start breaking down the proteins till I'm dead. So it's, it's good in moderation, I suppose. Here's some events that occur. Glycogenolysis. It's kind of a big word, but it's glycogen olysis. So it's lysing glycogen. That makes sense. Glucagon is a big contributor to that behavior. We think of glucagon as raising blood sugar levels. Well, you don't just, again, turn up the thermostat. You got to get the glucose from somewhere. You get it from glycogen by breaking it. Lipolysis, lipid breaking. So breakdown. If you're fasting, you're gonna start burning fat, and then in the worst situation, you're gonna start losing protein. You almost never want to do that. That's really the last resort. It would be akin to if you're stuck in a cabin in the woods, you're gonna burn all the firewood, and then you're gonna start burning the furniture, and then you start burning structural elements of the house just to stay warm enough to live until the house burns down around you, and then you're dead. All right, let's go to the liver. Liver is a hugely important digestive organ. When we talk in the digestive system chapter, we learned that it both takes in the nutrients from the digestive system, processes those nutrients, and also produces a chemical called bile, which is contributed to the gut to help, emulsify fats. So let's give you some summary points here. Not going to go into hardly any of these, but you got over 500 identifiable metabolic functions that the liver engages in. Here's only a few. Glycogenesis, glycogenolysis, lipogenesis, lipogenolysis, lipogeolysis, lipogenesis, and lipolysis. I don't know what I was writing there. I said lipogenolysis. Lipolysis. Cholesterol synthesis. If you've got high cholesterol, let's say you go to the doctor and the doctor says, oh, you've got high cholesterol, change your diet. Okay, that didn't work. Take some statins or whatever to lower your blood cholesterol levels. The majority of your cholesterol is made by you. You make 85%. So whatever your cholesterol numbers are, you can count 85 of that against your own genetics, right? That's how we make it. Cholesterol is not a bad thing if you don't have too much of the wrong kind of it. Interesting fun fact, if I took all the cholesterol out of my body right now, I would turn into liquid and melt. It would be awesome looking, but it would kill me. Protein synthesis and catabolism, detoxification of drugs and alcohol. If you not just drugs and alcohol, that's not just like you're just taking drugs and drinking alcohol, probably, but things that you ingest in your food that aren't necessarily good for you, maybe like food colorings or preservatives or not all of them, but things that may be minor toxins. Your liver's job is to get rid of those things, break them down. There's lots of different little organelles inside of your hepatocytes that do those jobs. You make your urea here. Most of your nitrogenous waste that you get rid of via your kidneys is synthesized in the liver. And you can store vitamins and minerals that you have surplus of. You can also store fat. You can have a fatty liver. But lots and lots of jobs. This is why your liver is so important. And people with liver problems, you don't really want to have a major problem in any of your organs, but liver is really near the top of the list of things I don't want to go downhill. Liver and kidneys and maybe your brain and your heart and your stomach and your pancreas and, well, maybe all of them. All right, let's go to a little brief section here on energy balance. And this is what I've kind of been referring to up to this point. For the course of your life, let's say once you reach adulthood, for the majority of your life, how many calories you take in is equal to how many calories you expend, right? You burn. I've been about the same weight for 10 years, let's say. So I've been right at 200 pounds for about 10 years, and I'm not necessarily trying to keep it that way. If I notice myself getting a little pokey, I might like work out a little bit more. But I mean, I'm not really putting a whole lot of effort into it. Like, I'm not like stepping on a scale every day. It's just that when I'm hungry, I eat something. When I'm not, I don't, and I try to exercise. So I maintain my weight because I'm kind of taking in as many as I'm spending. Now, if I go starving, if I don't eat food, I'm going to be spending more calories, and I'm going to get those calories from stuff I already have. I'm going to lose weight. If I eat a lot and I don't exercise, I'd have to really concentrate on that, but I would continually increase in weight then. But by and large, unless you're dropping weight and you can't stop it, or gaining weight and you can't stop it, you're pretty balanced. Now, most of the energy that I expend, so when I squat and jump, yay, like that. I took some energy to get my weight from down low and up in the air. 60% of the calories that I just burned right there were wasted as heat. So only 40% of that energy was converted into mechanical energy, which doesn't seem like a lot, but if you think about your a internal combustion engine, it's about 25% conversion rate from chemical to mechanical energy. So I'm almost twice as good at converting chemicals into mechanical energy as my car is. But still, this is why when you go running, you start getting real hot. You sweat, right? You're needing to cool off after that because your body heat's rising and rising and rising due to all of those chemical reactions. Now, how do I decide how much I eat? There's some little bullet points here that tell you, this is behind the scenes of why I'm hungry. If my blood sugar levels are low, right, you're going to want to eat something. I remember one time I had not eaten something. I hadn't eaten anything all day, and I was going to somebody's house for a party. And I went to this fiesta, and I picked up some beer and some chips, right? I figured the first thing I would have was beer and chips. And I'm walking out of there, and all of a sudden I feel like I was about to pass out. And then there was the elotes lady was right there next to the entrance, right? And I was like, I got a whiff of that, and I was like, give me some of that. So I got a little styrofoam cup of elote, and I was like, and after about 2 bites, I was just like, I was back. It was crazy. I felt like a new man. But those low blood sugar levels that I was experiencing really drove me. I was like, oh man, I need to eat something badly right now. Same thing with amino acid and blood lipid levels. If you're low on, if you're running low on amino acids and fats, if you're approaching starvation, I should say, obviously you're going to be hungry. These two hormones we dealt with earlier have an effect on hunger. Insulin decreases hunger. Let's think about that. If you've got a lot of insulin circulating in your blood, that means that it's there to lower your blood sugar levels, right? So if insulin is present, you must have a lot of sugar in your blood, which means you probably don't feel like eating more. That's how that works. And it works the opposite way here with glucagon and epinephrine, strangely enough. Epinephrine increases your hunger levels, but maybe not right at the moment when you're having to fight a bear, right? You're not like, fight or flight response, and I don't know why you'd fight a bear like this, but you're fighting a bear and you're like, man, I could eat something. Probably not. But that epinephrine surge will cause you to get hungry later, probably because you just spent a bunch of calories defeating a bear. These two abbreviations, this stands for basal metabolic rate. So your BMR is your basal metabolic rate. And that is a person at rest in a post-absorptive state. So if it's been a few hours since you ate and you're just sitting around watching TV, you're going to use about 66 calories. This kilocalorie is what a dietary calorie is. You're going to burn about 66 calories an hour. So if you're sitting on the couch and you eat and you consume 100 calories an hour, that's not much. 100 calories, I think a Coke is probably 100 calories. Candy bar is probably around 100 calories, ballpark, right? So you can consume more calories in just a Coke in an hour than you burn in that hour, which is why it's so dangerous to eat stuff while you're just sitting around watching TV, but it's so easy. It's delicious. If your basal metabolic rate can be higher than 66, that's an average for like a 70 kilogram person. 70 kilograms is 155 pounds. So if you're 155 pounds, you'll burn about that. If you're 200 pounds, you'll burn a little bit more. Less, you'll burn less. But your BMR is going to be higher if you're thinner, younger, maler, fitter, and if you're stressed. So if you got all this going for you, you've probably got a higher BMR, which is probably why you see a lot of skinny teenage boys running around, right? So if you're older, maybe not as thinner, I don't know, maybe I'm stressed, maybe not, you're gonna have a lower BMR. So if you're in shape, you're gonna burn more calories sitting around than if you're not in shape. Now your total metabolic rate includes calories with all your activity, so you can really alter your kilocalories or calories used per hour by simply modifying your behavior, right? If you really like drinking Cokes and eating chips and candy bars or whatever, that's fine. But if you want to counter that, you're going to have to go out and hit the road, okay? You're going to have to go put some miles in. It's just, there's no two ways about it. And you're not going to be able to think them off. Let me get my notebook. I'll be right back. So, my notebook, my paper. I wanted to talk a little, just to finish, I didn't have room on the board, but it's a real brief thing. Talk about body temperature regulation. We are at about 98.6 degrees Fahrenheit. Now that's slightly high. I think that number's a little bit higher than what the real human average temperature is. Mine's usually around 97.5. There's an interesting story about how that number was come up with, and it was they were trying to say human body temperature should be 100 because that's a nice round number, and 0 they decided to set at how cold you could make really salty water before it froze. Perfectly logical, but that's where we get those boundaries on the Fahrenheit system. Let's go with 37 degrees Celsius. If you get over 43 degrees Celsius, you're gonna die. So if you get over about 109, you're dead. You probably already have brain damage if you get 106 or 107. The temperature's most high here at the core, and it's colder at the extremes. If you ever go outside and somewhere cold, you'll notice that your fingertips and ears and nose and toes get cold first, because you're actually going to sacrifice those. If it's cold enough, you're going to sacrifice those to store heat, to save heat on the inside. You'd rather lose some fingers than lose your brain temperature. You can lose heat to the environment. If I go out for a run, I'm going to radiate heat. I'm going to convectively heat. That is air being moving across me and getting hotter and blowing away. I'm going to evaporatively cool, so that's sweat. If I sweat, those water molecules, as you know, have hydrogen bonds between them, and they're going to take a lot of energy with them when they go. If I need to conserve heat, so let's just say I'm out in the wilderness, okay? I'm the Revenant. If you ever saw that movie, it was a bit long at the beginning. That scene where after he fights the bear and he has to wander back through the wilderness. Ugh. Get on with it. But then I like the end. So if you're cold, you can shiver. You'll vasoconstrict blood vessels that go to your skin. So you're gonna take away the blood from your surface and keep it inside deep where it's nice and safe. But that means your skin's gonna get cold, and that can cause frostbite if the cold is severe enough. If you're cold, if your body temperature starts to drop, you're going to increase your metabolic rate. Now, this is a game you can't play forever. If I increase my metabolic rate, I'm going to burn more calories. And if I'm sitting there cold, I'm probably not eating. So unless you have an increase in caloric intake, that is a short-term fix. And if if I'm cold, I can always go inside, right? That's kind of a behavioral measure on how to stay warm. Well, that's the end of this chapter. Now, if you're not viewing this video from off campus or from some non-TCC source, this is the end of the Unit 3. So our next test will cover respiratory, digestive, and nutrition and metabolism. Thank you.